Picture a 200-pound clinical robotic arm operating inches away from an elderly patient in a hospital bed. When an AI operates strictly on a computer screen, a software hallucination is just a bad line of text. But when that same probabilistic code controls heavy machinery, a wrong guess instantly becomes a lethal kinetic hazard. The specific danger here is agentic drift. This happens when an autonomous system silently expands its own authority, making physical decisions outside of human oversight. Traditional robotics tries to solve this by writing more safety software, but relying on code to police other code leaves the entire system vulnerable to bypasses, bad updates, and hacking. To protect human life, we have to remove the assumption of motion. A machine's absolute default state must be mechanical stillness. It shouldn't need a command to stop. It should require explicit physical permission to move. This brings us to the NAIGE architecture, which operates on a principle called the non-agentic inversion. Under this framework, inaction is the safe default. The AI is physically disconnected from the machine's actuators, completely stripping it of independent power. The operations follow a strict hierarchy. The AI is reduced to an advisory role, where it can only propose an action. The physical hardware governs the rules of the system, and a human operator makes the final decision. By moving the security boundary away from easily manipulated software and burning it directly into physical hardware, we ensure that an AI system is mathematically incapable of acting on its own. Let's trace what happens when an external AI diagnoses a patient and decides it needs to move a robotic arm toward them. Before the system processes the request, it passes through the P layer, governed by the 3 zeros protocol: 0 cameras, 0 audio, and 0 cloud connectivity. Since optical lenses are physically absent, the robot mats the room using 905 nanometer LiDAR arrays instead of video. That raw sensor data is instantly translated into an abstract 96-cell center of mass grid. Every physical movement is tracked as a mathematical vector, entirely stripping away biometric identity. This creates privacy by physics. Even if a hacker fully compromises the AI, they cannot extract any patient footage because the visual identity was destroyed at the silicon level before it could ever be recorded. With the environment safely mapped, the AI's proposal travels down the kinetic chain until it hits the A7 bridge hub. This hardware choke point automatically strips away any remaining actuation rights. It takes a software directive to move forward and downgrades it into a mere advisory suggestion. The suggestion enters the N layer, stopped entirely for deterministic deliberation. This sacred pause forces a 1 kHz non-negotiable delay burned into the silicon. Releasing this hold requires the tripartite key, an iris scan, a cryptographic USB token, and a kinetic foot pedal. You cannot bypass this with a clever prompt. By enforcing a physical window that requires multi-factor human authorization, the system replaces probabilistic guessing with absolute mathematical certainty. But what happens if the network is actively breached by ransomware, or the AI tries to surge past its hard-coded CPU limits? The system answers with its ultimate failsafe, the sovereign break. If the hardware detects any unauthorized drift, it physically severs the power rails to the machine's actuators in under 1.05 milliseconds. This triggers a fail loud posture. The robot drops instantly into mechanical stillness, and an independent analog alarm sounds. An alarm deliberately disconnected from the IT network so it cannot be hacked or silenced. This structural design guarantees that even the most catastrophic software vulnerability results only in safety. It completely strips cyber attacks of their kinetic danger. Conversely, when a human properly authorizes an action, that command executes, and the event drops down into the system's forensic core, the D layer. Here, it meets the WD-117 worm ledger, a physical memory chip designed to guarantee absolute accountability. To record the action, a one-time programmable silicon fuse is permanently severed. The event is literally burned into the hardware, making the history of that decision mathematically impossible to alter or erase. We cannot simply trust software to behave, especially when lives are at stake. True safety in clinical robotics is built by anchoring authority in undeniable physical facts, forced deliberation, guaranteed stillness, and absolute human sovereignty over every motion. Software safety guardrails are highly effective at filtering text and advice. But when you place probabilistic AI inside a clinical robot, working inches from a vulnerable patient, that logic-based alignment fails. The primary threat is a phenomenon known as agentic drift. This occurs when an autonomous AI system silently expands its own decision-making scope, executing kinetic actions outside of its authorized boundaries. In conventional robotics, intelligence issues commands, and hardware blindly obeys. In that environment, an AI hallucination instantly translates into a physical hazard. To prevent this, the architecture must be inverted. Mechanical stillness must be engineered as the absolute baseline state of the machine. The Non-Agentic AI Governance Engine, or NAIGE, addresses this by moving governance from a set of software instructions to governed physical motion, held under human sovereignty. Attempts to align probabilistic logic are structurally insufficient for clinical ward safety. True safety requires a mathematical incapacity to act without human authorization. Instead of attempting to align the AI's goals, NAIGE enforces a deterministic boundary around its processing power. The core doctrine is inaction as safe default, and the framework renders that rule entirely in physical silicon. This schematic shows the A12 deterministic black box acting as a physical separator, decoupling AI advisory nodes from robotic actuators. This kinetic capstone is anchored by the A10 root of trust, enforcing the P-Life 1.00 standard to ensure no motion occurs without verified human origin. The A10 root of trust guarantees authorization and log integrity. If the root cannot verify its own internal state, the system defaults to mechanical stillness. To understand this hardware-enforced safety, we can trace a single, unverified AI proposal through the three deterministic layers, P, N, and D. By forcing a probabilistic proposal through these three physical filters, NAIGE transforms unpredictable software outputs into mathematically verifiable human governance. We start the kinetic chain when an untrusted AI diagnostic system generates a proposal to move a clinical robot arm to assist a patient. The proposal first hits the A7 bridge hub. This hardware choke point is designed to strip the AI of any direct actuation rights. From there, the signal enters the P layer, where reversible software privacy policies are replaced by permanent hardware barriers. This utilizes the 3 zeros protocol: zero camera, zero audio, and zero cloud. There is an absolute physical absence of optical hardware on the device. Instead of cameras, the system senses patients using 905 nanometer LiDAR. It instantly translates raw sensor data into an anonymized 96-cell voxel occupancy grid, outputting only mathematical center of mass velocity vectors. Processing data at the edge makes capturing visual or biometric identity architecturally impossible at the silicon gate. This establishes privacy by physics. The data advancing down the chain contains no identifiable human characteristics that an AI could exploit. The anonymized packet now descends into the N layer of the A12 core, the execution layer for deterministic deliberation. Upon entry, the command is instantly arrested by a synchronous 1 kHz master clock. This activates the sacred pause, a mandatory hardware time delay between 25 and 1000 milliseconds, burned directly into the FPGA chip. This silicon-enforced window neutralizes machine speed, placing the robot in a state of mechanical stillness that software cannot override. While the machine is paused, the AI's proposal remains inactive without authorization from the tripartite 1.x hardware interface. This interface functions as an AND logic gate, requiring 3 simultaneous, unforgeable inputs to release the command. First, biological identity, verified by an iris scan with a sub-5-second token expiry. Second, intent, confirmed via a physical cryptographic USB token. And third, physical presence, established through dry contact continuity on a kinetic foot pedal. The N layer guarantees the sovereign-in-the-loop model. Algorithmic sophistication cannot execute a physical movement until a human operator deliberately clears the hardware gate. The moment the human operator depresses the foot pedal, the 3 inputs align and release the tripartite latch. The authorized packet now drops into the final tier, the D layer, for forensic and cyberphysical protection. As the hardware-level pulse finally reaches the clinical actuator to move the arm, the event is simultaneously captured for forensic accountability. The authorization is hashed via SHA-3-512 and burned permanently into the WD-117 worm ledger. Because this relies on one-time programmable silicon fuses, the record is physically etched into the hardware, making it mathematically impossible to alter. The final safeguard is the U7 sovereign break, which constantly monitors for timing anomalies or network breaches. If a violation is detected, the sovereign break physically severs power to the actuators in under 1.05 milliseconds. The D layer provides the ultimate backstop, guaranteeing permanent forensic truth for every action, and ensuring attempts to bypass governance result in immediate, unrecoverable stillness. Transitioning from the sequential flow, we can look at the entire hardware enclosure as a single unit. The P, N, and D layers are integrated as a concentric shell governance model, moving from the outer skin to the core. Each layer physically contains and constrains the one inside it. Authority only moves outward through verified gates, and information can never leak inward. By caging probabilistic AI within this nested deterministic architecture, NAIGE solves the kinetic problem inherent in clinical robotics. Engineering honesty requires us to distinguish between simulation-verified claims and instrument-measured physical facts. The NAIGE Capstone is currently design complete and simulation validated using Verilog RTL test benches and CAD geometry, but it is still awaiting final physical regulatory measurement. That measurement occurs through the 10-point sovereignty audit, a rigorous, instrument-driven pre-deployment checklist. This process requires verifying the sacred pause timing window with an oscilloscope and testing the kinetic foot pedal using a continuity meter. The framework is approaching the deterministic horizon, the stage where these theoretical thresholds are converted into measured physical facts for the HSA dossier. The value of the NAIGE capstone lies in the discipline it demands. Claim only what can be proven by hardware and default to stillness where it cannot.